Welcome back. I got these display modules here in one of my recent mailbags, card link, and I built up 5 of them. There's a video for that too, card link, and now it's time to have a closer look at these. And there's some ground to cover here. First of all, I got the impression, and I might be wrong there, that these devices are sometimes described as having an I2C interface, and they do not have an I2C interface. Anyway, to clear that up, we will have a look what's exactly here on the board, what's the circuit, and have a look at the Chinese and Google translated datasheet of these things here. These things not being I2C was for me the deciding factor in choosing the Arduino library I'm currently using. And there are floating 2 out there. So we will talk about that too. Of course, we shall measure the current consumption of these things. I suspect them to be quite power hungry. I will show you the capabilities of the library I'm using, besides making nice patterns. And as the icing on the cake, I will try to run at least 2 displays at once on one Arduino. And discover the possibilities to run several displays. I only have 5 here now. So anyway, let's get started. So what do we have here on the board besides the TM1650 and a 100 nanofarad decoupling capacitor? We have 2 resistors here, which I suspect will be pull-up resistors to the SCL, and SDA line. So this should be here VCC. I have to put this the right way around because there is a diode in the way to the VCC pin. Too much. And the diode is really only in series with VCC to keep you from reversing the polarity. That's all. Let's have a look at the datasheet. I'm here at the bottom of page 1 of the Chinese datasheet, and my scribble here is just what we discovered on the board: the decoupling capacitor, the protection diode, and the 2 pull-up resistors for the SDA and clock line. Clock, not SCL like you would call it in an I2C device. Anyway, there are also 2 internal pull-up resistors here, at least in that schematic. And I tried to measure them on a naked chip, but depending on the polarity I applied with my ohmmeter, I came up with 41 meg and respectively 3.7 meg, between pin 3 and 2 and 2 VDD. So I highly suspect that these don't really exist, okay? And of course you have your 4-digit pins and your 8 signal pins, A to G and decimal point. It's driving the 4 digits in a multiplexed mode. And on the top half of the first page we find that statement here. And that statement reads, according to Google Translate, high-speed 2-wire serial interface. No mentioning of I2C. And on page 7, Google Translate again, we're talking about high-level output voltage and low-level output voltage, like run-of-the-mill totem pole logic output. No mentioning of open collector or open drain maximum currents, for pulling down the line that is pulled high by a pull-up resistor. So electrically not exactly I squared C. And you have to believe me, if you look at the software protocol, that thing is speaking, not Chinese, but either not I squared C, definitely not. For example, it doesn't has an I squared C address. It doesn't do I squared C device addressing on a bus. So definitely not I squared C. And finally, I wanted to show you the typical application picture. Please note these are 2 applications in one picture. You can also use that chip to decode a key matrix, okay? But we won't talk about that. But basically, you use it to drive 4 digits of 7-segment LED displays. And note here, they call it now SDA and SCL, like it's I squared C. And we saw in the other picture they called that line just clock. And also note, very important, besides the 100 nano decoupling capacitor, they also say you should add a 470 micro. That's missing from the board. We will have to investigate that further. That brings us to current consumption. Oh, it's beeping. Let me power the Arduino up here. And we see the current is rising. Let's take it a few more samples until it's... No, we got the maximum. So 95 milliamps, with all segments, including the decimal points on. That's a lot. Especially when you plan to utilize the tiny onboard 5-volt regulator of an Arduino Nano. According to the datasheet, this tiny thing can dissipate between 800 and 1600 milliwatts, depending on the layout, how much copper is there under the pins. But considering it's on the back of the board and the board is sitting on a breadboard and there's absolutely no airflow, I would probably err here below 800 milliwatts. And that means that you can, I think when you use a 12-volt supply, one such display might be enough to cook that regulator. If you use a 7-volt supply, then you have only a voltage drop of 2 volts to get down to 5 volts. You might connect 2 or maybe 3. I wouldn't connect 3. No. So be careful. Of course, if you are using USB power, so you get 5 volts in and just use that in your Arduino Nano, you might be fine connecting maybe 4. It's a trial and error thing. And those 100 milliamp supply current is probably also the reason why they want that 470 microfarad decoupling capacitor here in the power supply too. I expect ripple currents up to 100 milliamps when you really run that thing here. We might have to get out the oscilloscope. Let's talk libraries now. If you go into the Arduino library manager and you search for TM1650, it brings up this library here from Anatoli Arkhipenko. I probably butchered that name, sorry about that. And it's also available on GitHub. I'll put the link down into the description. And this is some code from one of the examples that come with the library, only the first few lines. And you immediately noticed it uses the wire library of the Arduino for the I2C bus, meaning you have to connect the display to the A5, A4 pin, I2C, SCL, SDA, and you can only connect one of those displays. And you probably shouldn't connect any other I2C devices to those pins, because as I mentioned, the TM1650 does not really speak I2C. It doesn't heed an I2C address, and it just listening to the bus, and whatever bit pattern appears here, it thinks it's for itself, even if you are addressing another I2C device. And that might lead to problems. So I searched for another library. And I found one on GitHub again from Maxint. And you have to install that library manually. Okay, but that's not too hard. And again, an example from that library. No wire. And when you initialize the object, you pass 2 pins. Incidentally, we are passing here the I2C pins A4 and A5. But we don't have to. So now that we know which library I prefer, let's dive in and see what that thing can do. And here is the first example for using that library. Please note the yellow clock line and the green data line. They are no longer connected here to the I2C pins, but to the digital 2 and digital 3 pin. And what we can observe here is one after the other segment in the digit is set. Then the display goes dark, and afterwards, display dark, it's dimmed, in 8 levels. And then the whole thing starts again. Let's have a look at the code. I obviously need the TM1650 library, and I instantiate one object, display 1, and in the constructor you can pass a lot of stuff. You can pass the data pin that you want to use. I'm using now digital pin 2, the clock pin, digital to pin 3, the number of digits in the display, if the display should be on or off, and what intensity the display should use. You can vary the intensity between 0 and 7. We will see that later. And which display mode. I'm using a 4x8 segment display, so that's my display mode. You don't have to provide all that stuff, because most of these parameters in the constructor, they have a default. So num digit 4, and the display will be active, and the intensity will be at a maximum of 7, and the display mode will be 4x8. And you see, I don't pass the last argument here because, I rely on the default that's defined in the class. Setup is empty. The interesting stuff happens all in the loop. First, I loop here through all my 4 segments, 0 until 3, and note digit 0 is the leftmost digit. Then in this loop over segments, I create in that segment variable here bit patterns 1, 1, 1, 1, 1, 1 until I reached 8 ones, and each bit corresponds to the segments A, B, C, D, E, F, G and decimal point. I use the method setSegments from the library to set these segments for a specific digit. Then I use the setup display method, which is not really a setup. You don't need to call that method before using the display. It has two parameters. The first parameter says if the display is active. I set that to false. Yeah, that was the time when the display went dark again. And you can also set the intensity of the display between 0 and 7. Yeah, I waited 1 second. For 1 second the display was dark. And then I go through the next loop over the intensity 0 to 7. Yeah, you saw that the display was dimming. And again, I use the setup display method. This time active is true. I want the display on. And I just vary or ramp up the intensity between 0 and 7. Yeah, then I clear the display and everything starts again. Quite simple. Of course, you can display digits and yeah, set the decimal point on or off at specific locations. And as soon as the loop is through, we will see that you also can display numbers with leading 0. And again, you can set the decimal point at a specific location. I only changed the code in the loop. And in the loop we have here the first loop that goes from 0 to 3. That is the position of the digit I want to set. Left to right again, as we have seen. And the inner loop here goes simply through the numbers 0 to 9, the number I want to display at that position. And yeah, to do that I use the set display digit method. First argument is the number 0 to 9 we want to display, then 0 to 3, the position at which it should be displayed, and then a Boolean that indicates if the decimal point at that position should be set. I'm simply using here the n modulo 2, which gives me a true for every uneven number and a false for every even number. And then, yeah, you don't have to care about that, but you could specify another font. I haven't found a use for that. It has a default, so I don't provide it. Little delay, and then I use a clear display digit method to clear the digit at that position again. And yeah, optionally, you can set the decimal point at that position too with that function. Second loop here, a little bit of bit banging. So dp is where I want to have the decimal point in my number, 4-digit number I displayed. And this is a bit pattern. I initialize it with a 1 to the very right, least significant bit. And then the next bits are decimal point position 1, 2, 3, 4, right to left. And I simply shift that bit to the left each time I go through the loop. In the inner loop, I go through the numbers 9, 99, 999, and 9999. And to display these numbers, I use that set display to decimal number method. Here is the number, obviously 0 to 9999. And this is the bit pattern where the decimal point should be. Delay, clear display, that's all. Finally, you can display, sort of text on that display. I mean, it's 7 segment, but arrow to the left, arrow to the right with a dot, no hope, SOS, rest in peace, and so on. To display some string, maximum 4 characters, you use the set display to string method. And you have also an argument bit pattern again, where you can set, at maximum 4 decimal points on the display. You have an argument position where you can define where the string should be started. Okay, 0 is leftmost. Yeah, my first arrow was to the left. And then you have this also optional fourth argument where you can specify the font. Never used it. Don't see any use for it. And yeah, the second arrow, you remember, was to the right, and I achieved that by starting at position 1. And please note the bit pattern here, yeah, a dot after the last R is the same. So the bit pattern you provide here is relative to the string, not fixed from the digits 0 to 3. I printed no, and also note I do a clear display in between, because that function, for example, printing NO, will only clear the data for digit 0 and digit 1, not digit 2 and digit 3. Hope we've seen that. SOS with 3 decimal points after each letter, and rest in peace with 3 decimal points, 1 after each letter. That's nice so far, but you might ask, do I have to do all the work if I want to display without leading zeros, with them, or negative numbers? And the answer is fortunately no. That's the code I just ran on my Arduino, and you see there are some changes here in the declarations. Up to now we just used the TM1650 class, which is by the way a subclass of TM16xx, and there are more subclasses to that supporting different TM16 chips. Now I added the TM16xx display class, which supports, let's say, advanced display methods. And you know already that setup here for my display, and then I have an object of the class TM60xx display, which I call display A, and that gets passed a pointer to my display 1, and for reasons unknown to me, I have to pass again the number of digits. In the loop, I only use one method from that TM60xx display class, and that is set display to signed decimal numbers. There are a lot of other functions to display unsigned numbers, hexadecimal numbers, binary numbers, and some more string functions. Anyway, that method here, it expects a signed long number. Again, we already know that bit pattern for the decimal points. And as a third argument, if you want to print the number with leading zeros or not. And again, fourth argument, that font I didn't find any use for, unless you want to create your own font. And this displayed obviously at the very beginning of my loop a 1 without leading zeros and without decimal points. Then I displayed a 1 without decimal points and leading zeros. You remember 0, 0, 0, 1. Then I displayed 9.999. Decimal point here at the leftmost digit. And then I displayed minus 999, decimal point after the first 9. That's simple. And no minus 1999 does not work. Now, why isn't that integrated in that base class here, TM16xx? And the answer is, that stuff here is supposed to fit into an AT-Tiny, these little 8-pin microcontrollers. Whereas that TM16xx display class is much larger, needs more flash, needs more memory, okay? And it's really powerful. It even supports the print object of or class of the Arduino. So you can simply say, display a dot print, and then use everything you can use in an Arduino print statement. And that brings us to the issue of using multiple displays. And as you can see, it works and it's quite easy. I just had to set up an additional clock and an additional data line to the second display. Let's see what's on the breadboard and then have a look at the code. Up to now, we had one display module on our breadboard, and I reordered the pins here. It's not the same like on the module. Have a look at the labels on the module when you connect your own boards. Just easier to draw that way. And the Nano, and besides 5 volts and ground connection, I had a data line running over here and one clock line. The clock lines on the breadboard were yellow. Yellow doesn't show very good on white paper. Now I just have a second display module and 5 volts grounds and a second pair of lines here. With data 2 and clock 2. In the code, I still have my display 1 object here with digital pin 2 as data pin and digital pin 3 as clock pin. And I added a second display 2 object, data pin, digital pin 4 and clock pin, digital pin 5. And I also instantiate a second display object, display B here, and set up as always empty. And in the loop itself, I have a loop counting from 0 to 999, and the first display, you saw that, displayed the positive number, where I am in the loop, and my second display, display B, displayed a negative number that is n, my loop variable, minus 999. Now, that's a wee bit wasteful. I mean, if I have 1, 2, 3, 4, or even n displays connected to my microcontroller and I have a clock and a data line per display, I need 2, 4, 6, 8, or for n displays, 2 times n pins on my microcontroller to communicate with the displays. Maybe we can do a little bit better. And indeed, we can. I have still my 2 displays here counting up and counting down. But if you look here, there are only 3 pins connected to my microcontroller. What I've done here is to share the data line between both displays. The displays still have their dedicated clock line, okay, but they use the same data line. And that's possible because the controller chip only reads data from the data line when it gets a clock signal. So as long as we have separate clock signals, we can share the data line. In the code, the only change is that now my display 1 and display 2 get the same digital pin 2 as data pin when I set them up. And that means with a clock per display plus a common data line, I need now for my 1, 2, 3, 4 displays 2, 3, 4, 5 pins on my microcontroller, or for n displays n plus 1. But we could, if we needed to, do even more better. There are these nifty chips out there called decoders or demultiplexers. These are the innards of a 74138 from Texas Instruments, I think a 3 to 8 decoder demultiplexer. And what that thing here does is you basically have your data input here. There are some disable pins too, we don't care about that, but your clock goes in here and it goes out at exactly 1 output here to 1 display. and to which display you select via these inputs here. So I have here 3 select inputs, 2 to the power of 3 is 8. So with 3 pins here, I can select 8 displays. So with a 2 to 4 demultiplexer, I can drive 4 different displays with 2 select lines, clock line and data line goes through. So 4 pins for 4 displays. With 5 pins, 3 select lines and a 3 to 8 demultiplexer, I can drive 8 displays. If I have a 4 to 16 multiplexer, I can drive with 6 pins 18 displays. And I've put that line here, and it's currently too hot up here to do the exact math here. You see the advantage. If I'm starting here at 5 displays, I would only need using a demultiplexer 5 pins instead of 6, and that goes up until I reach 16 or however many displays, and I need here only 6 pins, while I need here with my shared data line 17 and explicit data lines for each display 32. That's really a neat way to save pins on your microcontroller. And now it's time to get out the oscilloscope and have a look at that power supply line. I'm back to a single display. I didn't change the code though, and I disconnected the power rail to that display. The Nano gets its power from a cheapo USB power bank, and we can have a look now at the oscilloscope to get a feeling for the bass noise on the 5-volt rail. And as you can see, it's not really much. I mean, I'm between 5 and 4.68 volts with the peaks here that appear at some time included. So maximum peak to peak noise 320 millivolts, which is not nice, but good enough. And the main problem here is switched off, the output from this power bank. It's simply awful. Okay, I connected the display again, and you can already see there's a lot going on our 5-volt rail. Things definitely took a turn for the worse. I mean, my top line is still at 5.08 volts, okay, but my bottom line now, the peaks, they droop down to 4.28 volts, which is kind of unacceptable normally. I changed the code now using the set to string method to display 8888 and 4 decimal points, and immediately afterwards clear display. And these are the only 2 statements in the loop. So the display is basically flickering on and off with all segments and decimal points. And it got a little bit worse. So my upper cursor line is now at 5.14 volts and my lower one at 4.28 volts, giving me 80-60 millivolts peak-to-peak noise. This time I used the intensity parameter. I lowered it from 7 maximum to 4, and I only display once in the setup 8888 and 4 decimal points. And you see the noise is higher frequency now. That's because the little chip is using pulse width modulation to lower the intensity of the LED display. And also the peak-to-peak value is a little bit lower. I'm at the top at 5.1 volts, at the bottom 4.44 volts, gives me a peak-to-peak noise of 660 millivolts. The values we measured are of course completely unacceptable. I mean, we are here below the 4.5 volt limit for a 5-volt power rail, and that's the reason there's that additional 470 microfarad capacitor, yeah, for decoupling the 5-volt rail, beside the 100 nanofarad capacitor, which is actually on the boards. Let's get back to our worst case yet. So 8888 on off very fast, and see what capacitor we actually need to get that noise into a more acceptable region. Now I added a 470 microfarad capacitor, not an especially low ASR type, and long leads, breadboard, etc. And I'm back on switching on off the display with 8888 ... and you see something is happening. So our noise is down and we have now some lower frequency component in it. I guess that's the on-off stuff. And we are now at 5.1 volt at the top and 4.5 volt at the bottom. So peak-to-peak noise 600 millivolts. I added another 470 nanofarad capacitor, but the effect is negligible. So top line we are now at 5.06 volts, 4.5 volts at the bottom, leaves us with 560 millivolts peak to peak. I've added now two 150 microfarad capacitors, same series as the 470 I used before, and not much of a change here. If anything, things got worse again a little bit. Lower line 4.46 volts, upper 5.07, peak to peak 600 millivolts. So the manufacturer recommendation of 470 microfarad seems to be in order. They would have to add a low ESR, exclamation mark. If you have a look at the numbers, so without capacitor, completely unacceptable. With that 470 micro, still borderline, but then the one I used is not really a low ESR type. Anyway, 470 microfarad plus 470 nano, maybe an improvement, and 2 times 150 microfarad, things got worse again. So I guess 470 microfarad low ESR type. I take 2 points away from all this. First, the TM16xx library from Maxint is very powerful, very flexible, and it works perfectly. So I was just using the TM1650 subclass and that supplementary TM60xx display class for really displaying signed numbers, but I think it can accommodate any needs you can ever have with these kinds of displays. Second, the power requirements for these big LED 7-segment displays, they are demanding, 95 milliamps maximum what we measured for that one, and all the noise here, you need some decoupling on your power rail to keep things quiet. And with that I say bye.